Okay, let's go ahead and we'll start here. We're going to talk more about chemistry today. Anybody have any questions on anything to this point? Lab this afternoon is going to be, we're going to introduce the skeletal system. We're going to take a look at the skull. We are going to have our lab test next week in lab. So let's, any questions? Yes. No. Are you in? Okay. And that's fine. Yeah, you'll get a test too. So my Monday, whenever you're at somebody else's lab.
Somebody else's lab. I don't think my schedule lined up with any of the classes. Samuel. Really?
No, he's really fine. So, and unfortunately, it's too late to change. It won't matter. It's not going to hurt. Well, I hope that wasn't recorded. Yes, ma'am. Yeah, I'll take some time because going through the skull will take that long. I can take 15 minutes or so and go through the what to expect to see in the test. So that's a good question. Any other questions? So please don't ever be afraid to ask questions. And
I'm in your Monday lab, so do I take the test next week or do I take it the week after?
the week after.
Okay, I knew that you said it didn't line up with the
Yeah.
actual classroom. I was sitting there prepping this lecture on it.
Well, that's fine. You can, you'll take it when they take it, because they'll get the Monday lab will get the skull on Monday and next Monday. And then they'll have the test at the same time. Tuesday night. See, they always do this to us. They always have a Monday holiday to start the semester. And so the Monday lab always gets a weird schedule. And then if in the fall, we would normally have Labor Day in there and mess things up, but then we would get caught up sorta with fall break.
Yeah.
We don't have anything until spring break. So, but the advantage that the Monday lab has, it's virtual, so I don't need to worry about losing a day with the schedule. I can give the Monday lab their tests and still have class and not lose a day because your test will be open for 24 hours. Yes.
So wait, sorry, when is the test?
Lab test will be next week. So and it will only be, and I'll go over that in lab day. It will only be over the first two sections. It won't be over what we're doing today. Lecture test, it depends. When we get done with chemistry, and we're about over halfway through. When we get done with chemistry, then we'll pick a date for the test. But we'll just keep on going at lecture. So the test only covers, it's a unit test, so it only covers the material in the unit. So the first test is only on chapters 1 and 2. But I'll start talking about cells in chapter 3. So, any other questions? So, okay. And I'm assuming that everybody in Zoom can hear me, I hope. And I think I fixed the problem with the speakers here. So if you turn on your microphone and ask a question, I should be able to hear you. I did yesterday anyway, so that doesn't mean anything. So anyway, let's go into chemistry. And the last thing we were talking about, we just started talking about chemical reactions because we were talking about mixtures and we were talking about compounds. And that's correct. The lab test is next week, and the lecture test has not been scheduled yet. You're correct. So, okay. We're talking about mixtures and compounds. A mixture is just a physical intermixing of two things like sand and water or milk and chocolate, or tea and sugar. They can be physically separated because they're just physically mixed together. There are no changes. The properties in a mixture stay the same. The properties of the sand don't change when they're added to water. There's nothing about sand and water that's different. You can filter them out very easily. In compounds, the difference is there is a chemical change. When we combine carbon and hydrogen and oxygen, they share electrons and form sugar, for example, or any kind of carbohydrate. So we've had a change. The properties that we have after they're combined are different than the properties they had before. The properties of a molecule of sugar are different than the properties of the atoms of carbon and hydrogen and oxygen. These are chemical changes. These are compounds formed by the sharing of some way or another of electrons. And they form through chemical reactions. Chemical reactions is the last thing we were talking about on Thursday. The bonds between molecules are changed. They can be broken or they can be rebuilt. For example, if you take the ingredients for a cake batter, making a cake, you get the mix and the oil and the eggs and whatever else, or maybe you're doing it from scratch and it's got the flour and the sugar and whatever goes into it. And you mix all that up. It still hasn't become a cake. You could mix up the batter and leave it sit there and nothing would happen. You know, just let it just sit in the bowl. As long as you stop licking the spoon, it would just pretty much stay there. However, if you put it in a pan, put it in the oven and apply energy to it, you will now transform all those mixed ingredients into something new, because the cake is totally different than the batter. You know, it changes its property. If you mix, let me think of something else that you would, if you eat, that's a little too stretched. Let me think. Okay, who hasn't done, here's one. At some point when we were younger, we all discovered what happens with baking soda and vinegar. Everybody knows what baking soda and vinegar does. Who hasn't seen a baking soda vinegar volcano or done one for a science fair project? I mean, who hasn't seen, you know, where it comes up and it foams down over the side of the volcano and it's erupting, okay? That's a chemical reaction. You take the baking soda, which is sodium bicarbonate, and and baking soda is a base, and it combines with the acid in vinegar, which is acetic acid, and there's a chemical reaction that changes the components of the baking soda. Sodium bicarbonate's chemical formula is altered, the acetic acid is altered, and the end result is carbon dioxide and water and salt. That's what happens with, that's a chemical reaction. You have reactants and you have products. You take your baking soda, you take your vinegar, you get the foaming and the bubbles, and it's all exciting for a while. And then you have what's left, and you've given off a lot of carbon dioxide. That's what makes the bubbles. And you form a salt, and you've got water left over. So in any kind of chemical reaction, you are going to have reactants and products. And we end up with a compound that is different. We usually start out with a compound that is different from the reactants. It may be bigger, it may be smaller. We may have given off energy, we may have gained energy. So the reactants and the products. If striking a match is a chemical reaction. The chemicals in the head of the match combine with the chemicals on the side of the strip on the box. That's how they work. That's how those matches work. A match will not light if you strike it on concrete. Not most of them these days. The wooden matches or even paper matches. There's a chemical embedded in the strip that you strike on, and that those two, the chemical in the strip and the chemical in the match head, combine and into a reaction. And so it ignites. You apply mechanical energy to it by brushing them together, and you get heat and you get light and you get carbon dioxide coming off, and it burns up the matchstick, whether it's paper or wood, and now you end up with, that's a chemical reaction. Our bodies are based on chemical reactions. You eat something, you eat an apple, you eat something from McDonald's, you've got, Starbucks, if there are calories in anything we're eating, those calories are going to be released through a chemical reaction. The calories are usually held in some type of carbohydrate, an apple or an egg McMuffin, or the flavorings in your coffee, the creamer in your coffee, whatever is put in there that will contain calories within some type of carbohydrate, usually, or fat or protein, then we're going to have a chemical reaction to break those down to release them. Our bodies depend on releasing energy from carbohydrates, and it depends on protein to break proteins down to its basic component of what we call amino acids, so we can rebuild our own muscles with the new, with those amino acids. We sort of recycle amino acids. Amino acids are what we call the building blocks of protein. So if you eat a piece of beef or fish or chicken or egg or cheese or drink milk or whatever you have with protein in it, we break the protein down. We don't destroy it. We break it down to its amino acids, and we take those amino acids and we use that to build new proteins. So our muscles get bigger, or we have proteins for hair color, skin color, eye color, things like that. Reactants and products. And the reactants and products, we can either build up the product, or we get a product that has been torn down. But every chemical reaction is going to have a reactant, what it comes together, and the product. Now, there are 3 types of chemical reactions, what I started talking about with the other day. Synthesis reactions, combination reactions, where we take 2 reactants and combine them, and we get a product that is different. It's bigger, it's more complex. It usually takes energy. Baking the cake, that is a synthesis reaction. It's an anabolic reaction. Anabolic reactions store energy. There is more energy in a cake that has been baked than there is in the separate ingredients, and you bake that. There is when our bodies eat carbohydrates, once the cells have taken in all the sugar they want for energy, any excess sugar becomes stored in our liver as a very long chain of carbohydrates called glycogen. Glycogen, glycogen is sort of like the human version of starch. Starch that you eat a potato, it's full of starch, right? Everybody knows that. It's a starchy food. So is apple. Apples have the fruity area underneath the skin is all starch. It's stored energy for the apple or for the potato or the corn. If you like corn, the stuff that's inside the covering of the kernel, that's all starchy. Well, it's sugar. It's where the plant stores it. We don't store starch like that. We store our excess sugar in the form of glycogen. Glycogen is like the first cousin of starch. It's the human version of starch. So we take these little sugar molecules and we string them all together into a great big molecule, and we call it glycogen. And we store it, and we can draw on that later on when we need more energy. So a synthesis reaction is always going to build something up bigger. We call it an anabolic process. And we take energy. It takes energy to do this. We put energy into our system to build this up. So we build things up with anabolic reactions. We store glucose. Our proteins get bigger. Our muscles get bigger. You know, when you exercise and eat a lot of protein, your skeletal muscles get bigger. And if you don't exercise and don't eat a lot of protein, your skeletal muscles will shrink. We don't grow new cells. We just use the cells we have. The cells will enlarge or they're going to shrink. So that's an anabolic reaction. The other half of this is the decomposition reaction, where we're breaking things down. This is a catabolic reaction. We take large molecules and break them down into small molecules. And a catabolic reaction releases energy. So now we got this cake that you made, and you eat it. And so you have this cake. It is made up of carbohydrates, lots of carbons and hydrogens and oxygens, lots of stored energy in the cake. You know, the ingredients of that you use to mix the cake up had a certain amount of calories in the eggs and the oil and the sugar and the flour and all that. But now you stored energy in the finished product, and there are more calories available now in a slice of cake than there were in the individual ingredients. Plus, it's a whole lot easier to eat a piece of cake than it is to eat some raw eggs and some oil and flour and sugar. But then again, who doesn't like cake batter anyway, right? You know, so the point though is that we eat that piece of cake and we break it back down into its smallest components, and usually that ends up being carbon dioxide and water and the release of energy. Usually, whenever when we have a catabolic reaction, we're going to release energy, and we're going to give off carbon dioxide, which we breathe out all the time, and we're going to release water. So those are the three things that come out of a catabolic reaction: carbon dioxide, water, and energy. And so we eat the piece of cake, and we get the calories out of the piece of cake. Or you eat protein, and you break the protein down to its amino acids, or you break the fat down into very small particles, and we end up using those for different things in our bodies. Catabolic reactions. Anabolic reactions build up, catabolic reactions tear down. Anabolic reactions require energy, catabolic give off energy. Exchange reactions, the reactants and the products change places with each other. We build up and we tear down. So we take chemicals. An example of an exchange reaction would be if we eat protein, and we break the protein down to its amino acids, and then we make new protein out of those amino acids. So we start with protein, we end with protein. The protein that we started with is not what we wanted, and we end up with what we wanted, what we needed. We might make additional hair color. Hair color is a protein. Skin color is a protein. Eye color is a protein. The structure of our hair is a protein. All of the chemicals in our bodies that control reactions are proteins. And so maybe we take a piece of meat, which has all the protein in it. We tear that down to its amino acids, and we rebuild the protein to make an enzyme. And so we end up with a different product, but we had to go through a tear down and build back up process in these exchange reactions. Now, the last type of chemical reaction that we see here, and this is one that I didn't want to start on the other day. These are what are called oxidation and reduction reactions. We'll talk more about those when we get into the metabolism chapter. But what happens here in an oxidation reduction reaction, every time let's say if you burn something, you light a candle, the heat and light comes off the candle, but you're also releasing electrons. When you are burning the paraffin and the wax, you release heat, you release light, and you release electrons. And the paraffin is giving up the electrons. But those electrons have to go somewhere. When something is oxidized, when something is burnt, it gives off electrons. That's what enables it to give off energy. Something has to gain those electrons, and it's usually oxygen. So we say a compound gets reduced when it gains electrons. I know it doesn't sound right, but that's chemist talk. Our chemistry professor across the hall would say it makes perfect sense to him, but for people that teach in anatomy and physiology, when you gain something, how can it be reduced? But that's just chemist talk. But because when you give off electrons, when you're oxidizing something, you're releasing energy and releasing electrons. Those electrons are grabbed by another molecule, and it has become more negative. Those electrons are grabbed by another molecule, it becomes more negative. That's where the term reduced comes in. So oxidation and reduction. Every time we release an electron, it has to get captured by something. And that something is usually going to be oxygen. So anyway, more on that later on. I'll have some better examples. So, okay. If you're a chemical reaction, you have a choice. Well, you don't really have a choice. You're either one or the other. You're either an exergonic reaction, and that means you release energy. You light a match, you're releasing energy. You eat a Snickers bar, and you oxidize the Snickers bar, you release energy. Or an endergonic reaction. You eat some starch, you eat an apple, a potato, some fries, a piece of bread, a roll, it doesn't matter, and you convert that into glycogen. So you build something up. So, and you use up energy. It takes energy to store stuff. So you're either an exergonic reaction giving off energy, or an endergonic reaction storing up energy. Baking the cake is an endergonic reaction. It takes energy to bake a cake. Now, when you eat the cake, you break down the stored energy in there and release it so your body can do something with it. Exergonic and endergonic. Just think exergonic for exit and endergonic for entrance. Okay. Now, chemists will tell you that chemical reactions are completely reversible. You can start out with your reactants and get a product, and then reverse the reaction and go back to the reactants again. But that doesn't work in biological systems. It doesn't work in the human body. If you eat a piece of cake, some have this great desire for cake. If you eat a piece of cake and you oxidize, you burn the cake in your body to get energy, your body can't turn that back and get a new piece of cake out of it. It doesn't work that way, because chemical reactions, biological reactions are not reversible. We release too much energy. We don't have the energy, our body can't provide the energy to totally reverse that reaction. So, and plus the reactants have already been used up. We can't reverse the reaction. So in chemist world, yes, chemical reactions are reversible. In biological world, in A&P, chemical reactions are not reversible. We break things down. Sometimes the reactants are so tiny and we use them up so quickly that we can't reverse it. So what controls a chemical reaction? Well, there's a couple things that would normally control a reaction. Temperature. If you increase the temperature, you can increase the rate of reaction. I mean, you put a cake in the oven, is it going to bake faster at 200 or at 400? At 400, it's going to bake a lot faster than at 200. It may not be as baked properly, I have no idea, but it will bake faster at 400. So chemical temperature can affect it. Temperature usually increases the rate of a chemical reaction. Think about when you're making sweet tea. When do you put the sugar in? You make tea. When do you put the sugar to make sweet tea? When do you put the sugar in? Well, yeah, but at what point do you? When it's warm. The water molecules in, when you make tea, when you got the tea bags in the hot water and the water is hot or warm, that's when you add the sugar, because the sugar can go into the solution a whole lot easier when the water molecules in the tea are moving around faster. Otherwise, if you have a glass of tea that's cold, cold tea right out of the fridge maybe, and you add sugar to it, what's the sugar going to do? It goes to the bottom and form a sludge. My grandma used to love her a little tea with her sugar, because she put in, so much, it was like she could eat the sugar out of the bottom of the glass. But that's beside the point. The point though is that the chemical reaction was slowed down. She'd have this glass of iced tea with lots of ice in there and all this sugar at the bottom, because the sugar wouldn't go in the solution because the tea was cold. When the tea's hot, sugar goes in the solution easy. Temperature affects the rate of reaction. Usually things go faster, much faster at higher temperatures. The concentration affects the rate of reaction. And this is one of those cases where if some is good, more is better. The more you mix together, the faster reaction you're going to get. You do your baking soda and vinegar experiment, you're going to have a really the more vinegar you add to the baking soda, the bigger the reaction is going to be. It foams and foams, and it works. So the more you add, the bigger the reaction is going to be. If you sure, go ahead. So stick the doorstop in so you can get it back in. If you have a firecracker, a little tiny firecracker, we've all seen firecrackers, right? You light a firecracker and throw it, and it goes. It should be behind the door, the other side. Yeah. You light a firecracker and it explodes. It's not a big deal, it just goes bang. But what if you have a larger one? What do you have a bigger firecracker with more gunpowder inside of it? What's going to happen? It's going to explode. It's going to be louder. It's going to be a little more exciting, right? We've all seen that. More reactants. The more you have, the bigger the explosion is going to be. The louder the noise is going to be. So the more reactants you have, the reaction going to be faster and it's going to occur at a much faster rate. Particle size also affects reactions. Little particles react better than large ones. If you're making tea, are you going to drop a 10-pound block of sugar into, you have like at McDonald's to make the tea, they have those big containers of the teas in. Are you going to drop a big block of sugar into that and let it dissolve, or are you going to put in the powdered sugar, which is going to dissolve faster? Well, obviously, the little tiny piece. You're not going to throw a block of sugar in there. Large particles don't react as quickly, so we want to have small particles. So we have the smaller the particle size, the better the reaction is going to be. Now, in our bodies, we have a problem. Our bodies are stuck at 98.6. So we can't affect temperature to make chemical reactions go faster. We can't warm people up to make them more efficient. There's laws against stuff like that. So we can't do that. So we have to, all chemical reactions have to work at body temperature. And the concentrations are so tiny that there's not, and we can't affect that either. The amount of chemical reactants we have in our bodies are maybe just at the level of one molecule. And of course, particle size, they're very tiny in size too. So we cannot affect size or concentration or temperature. So we use something else. We use a protein that functions as a catalyst. A catalyst is a molecule that makes chemical reactions go faster. So, for example, if you had a charcoal grill and you pour your charcoal in and you throw a match on it, just plain old charcoal and throw a match on it, nothing's going to happen, right? Unless we're not talking match light, we're talking just plain ordinary charcoal. You throw a match on it, it's not going to start, is it? Probably not. You could be throwing matches on it all day long. However, now if you soak it with starter fluid, lighter fluid, what's going to happen? Exactly. If you soak it with nut, you're going to lose your eyebrows. Not that that's ever happened, but you know, it's always a possibility. The point is, though, that the lighter fluid, the starter fluid, is the catalyst. It makes the reaction go faster. Our bodies use catalysts. We use enzymes to make chemical reactions work at body temperature with small concentrations and small particles. The enzymes give us an assist. Without enzymes, we couldn't do anything. And so, when you're adding something like starter fluid to a charcoal grill, that's the catalyst. I mean, you hear about laundry detergents that have enzymes in there. You've probably all seen stuff in advertising there. The enzymes theoretically make the chemical reactions of removing the dirt from the clothing work faster and help to remove stains. I guess it works. I don't know. It probably has some beneficial reaction there because apparently it works better than just regular detergent. Anyway, now, so when we look at the body, our bodies don't necessarily play by all the rules of chemistry because we can't do anything about chemical reactions. Chemical reactions are not reversible in the body. Chemical reactions have to proceed regardless of the temperature. Are stuck at a constant temperature with tiny particles and very small concentrations. So we have to play by our own rules. We have to have an assist with the enzymes. Now, when we look at the chemistry in our bodies, we refer to it as biochemistry. And it's a whole field of study on that. Later, if you ever, go on to other, into more advanced classes, you could take numerous courses in biochemistry if you wanted to. Biochemistry looks at the chemical reactions that take place in our bodies. And we have two types of chemical compounds. We have what are known as inorganics, the inorganic compounds. And those are the things like water and salt, the acids, the bases, things like hydrochloric acid and sodium bicarbonate. That's an acid, that's a base. Carbonic acid is an acid, and sodium hydroxide is a base. All of these are what we call the inorganic compounds. They don't contain carbon. Water doesn't contain carbon. Salts, sodium chloride doesn't contain carbon. Hydrochloric acid and sulfuric acid and sodium bicarbonate, baking soda, doesn't contain carbon. So all the inorganic compounds are carbon-free. They're carbon-free. There are only two exceptions to that. And the exceptions are carbon dioxide. CO2 is an inorganic compound, and carbon monoxide. CO, and this is carbon dioxide. Carbon dioxide is stuff we breathe out. It is an inorganic compound. It is the is one of the two exceptions to the rule about no carbon in an inorganic compound. Carbon monoxide is the product of combustion. It's the stuff that forms when we burn fuel. It's the stuff that kills people when their furnace goes out, or they have a power failure and they get a generator and run it in their garage, and they breathe carbon monoxide gases and it kills them. Carbon monoxide apparently has a greater desire to bond with hemoglobin than oxygen. So the red cells that normally would carry oxygen for us, the carbon monoxide pushes the oxygen out. So they're carrying, instead of carrying oxygen to the body cells, you're carrying carbon monoxide, which the cells can't use, and the cells start dying, and eventually you die. So, and just recently, there have been numerous stories in the paper just recently in the news about people, whole families dying because of this. Not around here, but in other areas. So, okay, now let's, on that cheery note, let's go on to the organic compounds. The organic compounds are the carbohydrates, the starches, the breads, the pastas, things like that. The things that we like to eat, among other things. The sugars, the simple sugars, the table sugar, the compound sugars, the starch itself. We go, glucose is the simple sugar, and sucrose, the stuff we add to our coffee or to our tea, is a double sugar. And then we have the starches that we get in a potato or an apple. Fats and proteins and the nucleic acids, the DNAs and the RNAs. These are all organic compounds. They all contain carbon. They're all relatively large molecules, and they're all held together with covalent bonds. But with not discounting the inorganics, we need water. We'll be dead in 3 days without water. We need salt. We got to make our body run using salts. Salt, sodium and potassium are very important salts for us. We have to have. So we depend on that. We depend on acids. In our stomach, we have hydrochloric acid that's used to break down protein so that we can get the amino acids out of it. So we have to have acids, and we have to have bases so that we can neutralize our blood if it gets too acidic. So inorganic compounds have a very important role to play, despite the fact that there are many, many more organic compounds. So, got to have both of these. Now okay, the inorganic compounds. Take a look at water. Water is the most abundant of the inorganic compounds. Most of our cells are filled with water, or filled almost full with water. Our bodies are between 70 and 80% water. And depending on our age, an elderly person may only be about 40%, 45% water. A baby may be close to 90% water. We're probably around the 70% range in here. The reason, I probably said this before, the reason that old people wrinkle, we all know what I'm talking about, their skin's wrinkled, is because of loss of water. So now water has some unique properties to it. It has a high heat capacity. If you've ever tried to boil water, you know what that means. Water can absorb a lot of heat before it starts to break apart. When water is boiling, we've all tried to boil water at some point. Right? Everybody's, or at least seen water boiling at some point. It doesn't happen instantaneously. You can just look at it, it's like it's not boiling. And finally, you get a little bubble at the bottom of the pan, and oh, look, it's starting to boil. An hour later, it's like it's finally boiling. It takes a lot of energy to get the water to boil. That energy causes the bonds that are holding the water molecules together to break apart and reform, break apart and reform. It takes a lot of heat to do that. So water can absorb a lot of heat. This heat of vaporization, this is what keeps us cool when we sweat. We can pull a lot of heat off of our bodies thanks to water going from its liquid state to its gaseous state. It is a wonderful solvent, but it is polar. It has positive and negative ends, and that makes it easy to break apart salts and get the salts to separate. Water deals a lot with reactivity because we make solutions out of water, and we have lots of water in our fat cells to cushion our body. And a lot of organs in the abdominal cavity have no protection other than a layer of fat, like our kidneys set up high here right below the ribs, and there's nothing protecting our kidneys except a layer of fat around them and some muscle. That's all. Not like the brain inside the skull or the heart and lungs inside the chest. The kidneys and all the viscera have nothing except maybe some cushioning of fat. So, okay. High heat capacity, I mentioned this, absorb and release heat with little temperature change so that we don't see sudden swings in body temperature. When we get warm, we sweat and cool down. When we get cold, we shiver to warm up. But water can absorb a lot of changes in temperature so that we maintain a constant. Water doesn't, our bodies don't like to fluctuate. We're not like what is it? Did you see in the news about the iguanas falling out of the trees in Florida? It's so cold that the iguanas, which are, they are, what's the term? Poikilotherms. They say cold blood. They're not really cold. Their body temperature is air temperature essentially. And when it gets cold enough, they just stiffen up, falling iguanas, right out of the tree. They don't die. They just go into a state of dormancy, if you will. So we don't have any iguanas around here except as pets, probably. So, but I can't imagine having an iguana fall out of the tree while you're just thinking like, hey, look at that, So anyway, so water keeps us from things like that happening to us. So because water takes a lot of energy, it keeps us, helps maintain homeostasis. I haven't said that this week yet. So water keeps us cool through evaporation. It dissolves things like salts. It forms protective layers around our proteins. And of course, the big thing that we use with water is our blood. Plasma in our blood is salt water. 55% of our blood is salt water. So we depend on that to carry the red cells, carry the white cells. When the plasma leaks out of the blood vessels, it's carrying the sugars and the salts and the other proteins and the hormones that the cells need. So it's a medium for transport too. So that's why water is so important to us. All this cushioning and transport and cooling and maintaining a constant temperature and dissolving all sorts of solutions here. Now, salts are inorganic compounds. We depend on salts. Salts will separate out into their positive and negative ions. Remember, ionic bonds form salts. It's like table salt, sodium chloride. The sodium ion is the positively charged ion because sodium has given up an electron. Chlorine grabs the electron. Sodium now becomes positive, chlorine becomes negative, and they are joined together electrostatically with an ionic bond. It's like a magnetic attraction. The positive and negative ends of the magnet come together, and they're held together, and it's a pretty weak bond. Now, if you put table salt into plain old water, plain ordinary water, it will dissolve instantly because the sodium ions and the chlorine ions are immediately attacked by the water molecules. And the positive sodium is grabbed by the negative end of the water molecule. And it's pulled apart from the sodium chloride. The chlorine is grabbed by the positive end of a water molecule. Remember, the water molecule has the hydrogen ends of a water molecule are positive and the oxygen end is negative, and we pull the salts apart. Water is polar, and something that has these real strong positive and negative charges there can be just pulled apart easily. That's why salt goes into solution so quickly. And this works for any salt. Sodium chloride, potassium chloride, calcium carbonate, magnesium chloride, any salt that our bodies use can be pulled apart like this. So they separate out very easily. Now, chlorine is not real important to us. Chlorine is not a player here for it. It doesn't have a lot to do. The sodium is very important. The potassium is very important. We keep sodium on the outside of our cells and potassium on the inside of our cells to establish a charge on the surface of the cell. And that's how we generate nerve impulses and how we contract our muscles and things like this. So these sodiums and potassiums become what are called electrolytes. They actually carry a current. You probably heard me say this, that muscle cells have a charge of minus 90 millivolts on their surface. And nerve cells have a charge of minus 70 millivolts. And that electrical charge, which is measurable, comes from the presence of sodium ions and the potassium ions. These are electrolytes, and they have a constant current going through here. So we are definitely electrically charged. The most important of the ions that we use, these electrolytes, are going to be sodium, potassium, calcium, and iron. Iron is in the center of our hemoglobin. One iron atom, one iron ion can carry 4 oxygens. So we have about 1 million hemoglobin molecules in each red blood cell. So that's 4 million oxygen molecules it can carry. Sodium and potassium, I mentioned that. Calcium. Calcium is substitutes for sodium inside the heart, and calcium is also used in our skeletal muscle to allow contractions to occur. So we have to have a lot of these ions present. It's always going to be about sodium and potassium and calcium, and to some extent iron too. So we have these electrolytes are very, very important to us. Now here's what happens when you take salt and put it into water. The water molecules with their positive ends are going to grab the negative ion. So the water molecule is going to grab the, you can see here, there's a water molecule. Here's a water molecule. The hydrogen ends are positive and the oxygen end is negative simply because the nucleus of the oxygen tends to draw the electrons down toward it. So the electrons are more skewed in this direction, so that we have 10 electrons here, and we generally pull them down a little closer to the oxygen, which makes this slightly negative and makes the hydrogen end slightly positive, and we call it a polar molecule. Stop that. There we go. Call it a polar molecule because it has a positive and negative end. And of course, our sodium and chlorine, sodium is positive, chlorine is negative, and chlorine is attracted to the hydrogen end, and the sodium is attracted to the negative oxygen end, and it just rips the salt right apart. It disassociates completely. That's why salt goes into solution so easily because of this. Okay, now, you can see how, there's sodium chloride right there, and here comes the water molecules grabbing the positive and negative ends. A little better than my drawing, but so there we are. Another type of electrolyte that we have in our bodies. Electrolytes are substances that can carry electrical charges. Acids and bases are electrolytes also. Acids are what we call proton donors. They give off hydrogen ions. The hydrogen ion, like hydrochloric acid, will separate out. It will dissociate into the hydrogen ion and the chlorine ion. And the hydrogen ion is called the proton, because the hydrogen ion, if hydrogen loses its electron, all that's left is the proton. If we take a look here, here's your hydrogen ion right there. The protons in the middle, the electrons out here, and that would be written as just hydrogen. But if we get rid of the electron, if the electron's gone, then all we have left is the proton. And so we call the whole hydrogen ion, H plus is called a proton because the electron's gone. Just trust me on that. Now, acids are going to be proton donors. Every time an acid goes into solution, you're going to break apart into usually a hydrogen end and then the negative end, whatever, like hydrochloric acid will give you the hydrogen ion and the chlorine ion. Sulfuric acid will give you the hydrogen ion and the SO4, because it's H2SO4. So it will break apart and give you the positive and negative sides. Some of the most important acids in our body is hydrochloric acid, found in our stomach. We use it to break down protein. Acetic acid, which is essentially what we find in vinegar. Carbonic acid. Carbonic acid is what tells our brain to make us breathe faster. When we exercise, we give off carbon dioxide. We burn sugars for energy and we give off carbon dioxide. The carbon dioxide level starts to rise. How does our brain know that? Because we don't monitor CO2. The brain monitors the acid and base level in our blood. That's easier. Carbon dioxide being generated from the breakdown of sugar combines with the water in our plasma and forms carbonic acid, makes our blood a little more acidic. And our brain picks up on that and says, hey, we're getting more acidic. We had better breathe faster, not to get more oxygen, but to blow off the CO2. The driver for breathing rapidly after exercise is not the need for oxygen. So we got a boatload of oxygen. We got more oxygen than we need at any given time. It's to get rid of the CO2. So every time a blood cell goes through the body, it only gives up a red cell. It only gives up 20% of its stored oxygen. There's way more oxygen available. We only use a little bit every time it goes around, but we recharge it back to 100% every time it hits the lungs. So it isn't about getting more oxygen. It's about getting rid of the CO2. So, and that's a very important gas there for regulating our breathing rate. It's a whole lot, our brain finds it's a whole lot easier to measure pH, the acidity level, than it is to try and figure out what the carbon dioxide level is throughout our body or the oxygen level. Now, bases are proton acceptors. Sodium hydroxide is a base. It grabs protons, and then it becomes, the more protons it grabs, the more neutralized it becomes. And when a base goes into solution, it releases the hydroxyl ion. If you consider that what we're talking about with this hydroxyl ion, consider a water molecule, H2O will yield the hydrogen ion plus the hydroxyl ion. This is the hydroxyl ion here. The two of those combine to form a water molecule. Bases love to suck up this stuff. This is the proton here. So when when a base grabs a proton, it will usually give off this hydroxyl ion. Anyway, let's move on here. So why do we care? Well, the reason we care is because our bodies are designed to work in a very narrow range of what we call pH. The pH scale is a measurement of the acid-base concentration in our bodies. And we like to stay right around pH of 7.4. 7.4 seems to be the magic number for us. And what does 7.4 mean? Well, 7.4. pH scale goes from 0 to 14. Neutral is 7 right there. And you would think that we want to be at neutral, but we don't. Our ideal pH range is 7.4. It's a measure of the concentration of the hydrogen ions in solution in our blood. And the more hydrogen ions we have in solution, the more acidic we are. Now, this is what that means is, well, here's the statement that is very, this is not a fun statement. The pH is the negative logarithm of hydrogen ion in moles per liter that ranges from 0 to 14. Okay? Right, makes perfect sense, doesn't it? Well, to be perfectly honest, I don't think I've ever had anybody recently ask me about the negative logarithm of hydrogen ions, probably when I was taking a course or two in grad school. However, what it means is that a pH of 7, here's your pH scale right here, there's 7. If you have something that's pH of 7, its number of hydrogen ions and hydroxyl ions are balanced. You know, same number of hydrogen ions here equal to hydroxyl ions over here. However, if you go down to a pH of 6, pH of 6 has 10 times more hydrogen ions than a pH of 7. A pH of 6 is 10 times more acidic than a pH of 7. So this is when we say it's a logarithmic scale. So the pH of 6 is 10 times more acidic than 7. A pH of 5 is 10 times more acidic than 6. 10 times. And now it's 100 times more acidic than 7. So we go, every time the hydrogen ion concentration increases, pH drops. If we go to a pH of 4, that's 10 times more acidic than 5, 100 times more acidic than 6, and 1,000 times more acidic than 7. And eventually, if we get all the way down to 0 or 1, we are very, very acidic. You know, if we are, you know, because if pH of 1 is 10 times more acidic than 2, 100 times more than 3, 1,000 times more than 4, and so on. So we get down to the low end of the scale, pH of 0 or 1, and we are very, very acidic. Conversely, going up the other side, as we get close to 14, you know, a pH of 8 is 10 times more basic than 7. A pH of 9 is 10 times more basic than 8, and 100 times more basic than 7, and so on. So when you get up to pH of 14, you know, you're dealing with something like oven cleaner or sodium hydroxide. pH of 0 or 1 is hydrochloric acid, very concentrated hydrochloric acid. So, we keep our scale. The scale goes from 0 to 14, and in the human body, we try to stay right about 7.4. We want to be slightly basic because, see, we're always making carbon dioxide, which is always forming carbonic acid and always trying to make us slightly more acidic. So we like to be right above 7.4, but it is such a sensitive scale that the range for survival in our bodies goes from 7.45 to 7.35. It's a very narrow range. If we get out of either range, we're in big trouble. If we get below 7.35, we start having some serious trouble. Generally, we get down to like 6.8 or 6.9, which doesn't sound like a lot of difference. That's usually fatal. The same going uphill, going 7.5. We're usually dead at that point, or in big trouble. So our scale is a very good way of telling us, just how, what is the state of the body. If you have a patient that has a whole series of unknown symptoms, one of the things you would do would be get blood work on them to see not only, red count, white count, oxygen saturation levels, but also blood pH. Because if there's something wrong in the pH, something wrong where they're retaining too much CO2 or they're not retaining enough, it's going to show up immediately in the pH. And there's lots of situations where you might encounter something with that. So it's one of those practically non-invasive, take a little sample of blood, practically non-invasive test. You get the results right away just to see what's going on. The scale, okay. I think I've mentioned this already. Acidic solutions go from 0 to 6.99. Neutral is at 7. Distilled water is 7. pH is 7. Our bodies are going to be 7.4. The alkaline scale goes from 7.01 to 14. So we stay slightly alkaline in here. And there's the scale right there. 0 through 14. Sodium hydroxide, oven cleaner at the high end of the scale, very, very alkaline. Sodium hydroxide, I remember this when I took general chemistry. One of the first things they showed us was just how dangerous sodium hydroxide was. It would come in pellets, and they'd give you a pellet to hold in your hand, and it wouldn't hurt. But after a while, the skin would feel slippery, and the sodium hydroxide, I tried to do this before, was dissolving away the skin and releasing the fats in the surface of the skin. It was getting slippery. And I thought, okay, and that drives home that they're not going to pour hydrochloric acid on your hand, but it just to show how powerful it was. It didn't hurt, but it was dissolving the skin. So very, very powerful. I've actually had hydrochloric acid eat away my clothing in a chemistry lab. Where you spice something on your hand, and what's your first reaction? You get something on your hand, you try to wipe it off, right? So I just, I'm not thinking, I just wipe it off like that, and the next thing I know that my jeans are just disappearing. So because the hydrochloric acid didn't burn, because it wasn't that strong, but it was strong enough to eat away the fabric. So you take these chemicals seriously. Now, we're never going to do anything like that in here, but you don't know where you're going to be in 5 years and what you're going to be doing. Our bodies like to stay right around 7.4 because we're always going to be producing carbon dioxide. As long as the cells are alive, we're going to produce carbon dioxide and create carbonic acid. That's what they do. And we're automatically neutralizing that carbonic acid that gets formed, but we have to stay within this very narrow range in here. So, and just examples of some of the things that we see. If you like lemon juice, it has a pH of 2. Wine is 2.5 to 3.5. Coffee is around 5. Blood 7.4. An egg white is slightly basic. Ammonia is around 11. And of course, if you have oven cleaner or anything like that, it's very, very basic. So, okay. In our bodies, we're always going to be trying to neutralize acids and bases so that we can maintain our constant pH. We have these neutralization reactions. And every time we neutralize an acid and a base, the end result is going to be usually a salt, usually sodium chloride, and always water. So what our bodies like to do is take a strong acid like hydrochloric acid and convert it to a weak acid like carbonic acid. Carbonic acid is a very weak acid here. So it's easier for us to break down the strong acid because we have hydrochloric acid in our stomach. So we keep that in control by neutralizing it as much as we can, forming carbonic acid. Usually we may use sodium bicarbonate that our bodies produce, baking soda, and we neutralize the acid with the base, and we can get carbonic acid, or we can just get salt and water. Our bodies depend on what we call buffers to break down, to stop these acids and bases from causing problems. Again, we don't like to see any sudden changes in our body's pH. So we neutralize the acid, or we neutralize the base. We can convert a strong acid to a weak acid, a strong base into a weak base. And the most important system that we use for buffering, and we're going to hear a lot more about this in AP2, is the carbonic acid bicarbonate system. Carbonic acid, we convert hydrochloric acid to carbonic acid. So we break down the strong acid to a weak acid, then we neutralize it with sodium bicarbonate. We use sodium bicarbonate. We'll form, when we neutralize a strong base to a weak base, we'll take it from sodium hydroxide to sodium bicarbonate, and then neutralize it with carbonic acid. We call these buffers because our bodies don't like to have wide swings in pH in either direction. We like to stay right around 7.4. Our bodies can't survive if we get outside of these ranges. Now, organic compounds. I think this is the more interesting aspect of this. The organic compounds, the biological compounds, anything that contains carbon. There's a whole field of chemistry called organic chemistry, which is really just carbon chemistry. With organic molecules, we share electrons. It's all about sharing the covalent bonds. We don't ever lose electrons. We never, we don't have any electrons being stolen from sodiums and added to chlorines, for example. This is not ionic bonding or hydrogen bonding. This is all about covalent bonding. And the organic compounds are the carbohydrates, the lipids, which are the fats, the proteins, and the nucleic acids, the DNAs and the RNAs. They're all called polymers, means they're long chains of molecules. So they'll have a lot of carbons linked together. You would see a polymer would be, if you have a whole lot of chains of carbons linked together with hydrogens attached, like this, all held covalently. Why did I make it so long? There. I don't know what it is, but it's a long chain of carbons. And that's a polymer. Polymers are made up of small subunits. Amino acids are the subunits of protein. So a protein is a polymer. A polymer is a long chain of molecules linked together. Starch is made up of millions of glucose molecules linked together. In this case, the glucose molecule is the subunit, the monomer to link together here to make this long chain called polymer. And so let's take a look at the carbohydrates. We like carbohydrates. We like to eat carbohydrates. They taste good. These are all the sugars and the starches, the ones that we like. For example, we like sucrose. It's what we put in our coffee. We like glucose. We don't pay attention to glucose much, but if you drink, if you like a Coke or a Pepsi or a Mountain Dew, and they are sweetened with high fructose corn syrup, which most of them are these days, the fructose is a variation on glucose. So while we usually don't eat glucose per se, if you like a Coke, you know, you're getting like the first cousin of glucose when you get the sweetener in a Coke, because it's fructose. It's just a variation on there. Apparently, corn syrup is cheaper than regular sugar. Who knew? So a carbohydrate always contains carbon and hydrogen and oxygen, and it's always in a 1:2 to 1 ratio. It has 1 carbon for every 2 hydrogens and 1 oxygen. So you have a carbon, 2 hydrogens, and an oxygen, 1:2 to 1. So like glucose, for example, glucose has a molecular formula of C6, that's 6 carbon atoms, 12 hydrogens, there's 1:2, and 6 oxygens, 1:2 to 1, with the carbon, the hydrogen, and the oxygen. They always have this arrangement. There's whatever number of carbons you have, you're going to have twice as many hydrogens, and you're going to have the same number of oxygens as you have carbons, a 1:2 to 1 ratio. We use glucose as our fuel in our bodies. You can eat sucrose, you can eat sugar. You put it in your coffee. It's in various foods. If you go down to Krispy Kreme, you can see the donuts passing through and see the liquid sugar pouring down across. Anybody ever see that? It's just like pouring down across the donuts. It says it's liquid sugar. Well, that's sucrose. It's not glucose. I hope it's sucrose. I think it's sucrose. Everything we eat, every carbohydrate we eat, when we go to use it for energy, we have to break it down into glucose. Glucose, the simplest form of sugar, is what we use for energy. Everything depends on the presence of glucose. And so whether it's sucrose or lactose, which is milk sugar, or starch, like a potato or an apple, or a donut or cereal or anything along this, or bread, we're going to take those sugars, those complex sugars like the starches and the sucroses, and we're going to break them down to glucose. And that's where we get our energy from. We get it from the simplest form of the sugar for us. Now, the other place we see sugar, carbohydrates, are in the DNA and the RNA. The backbone of the DNA molecule is a sugar called a ribose sugar, a 5-sided sugar, 5-carbon sugar. RNA and DNA use this 5-carbon sugar as their structural support in their chain. You'll see it when we look at DNA molecules. The sugar that we eat is that we use for energy. Glucose is C6H12O6. It's usually a ring of 6 carbons, something like that, with oxygen sticking off on the side with hydrogens and stuff like that in a ring. The DNA has a 5-carbon ring like this. So we call it a ribose sugar because it's only got 5. I don't know why ribose is split. Anyway, we don't use that sugar for energy. We only use glucose for energy. Glucose is our energy source. Now, 3 types of sugars. Monosaccharides, the simple sugar. 1 glucose, 1 fructose. These 6-carbon sugars, 1 glucose molecule is a monosaccharide. It is the smallest of the carbohydrates. We generally don't eat glucose in the sense that, in the food that we eat, we're generally not getting glucose, if you will. We usually like to eat disaccharides. Sucrose is a disaccharide. The table sugar the stuff you pour into your coffee, the stuff that comes in the packets on the table. That's why they call it table sugar. The stuff that comes in the bag, you know, from Domino's or Food City. You know, the sugar is all the same. The only difference in sugars is it's either says pure cane sugar on the label because it comes from sugar cane, or it's called pure sugar because it comes from sugar beets. You can't tell the difference. Pure cane sugar versus beet sugar. They all look the same. That's sucrose. That's a disaccharide. That's the stuff we use, we put in our cereal. It's the stuff we put in our coffee, the stuff we use in baking. It's a very common sweetener. The monosaccharide is the sugar that our bodies use. And if we eat sucrose, we're going to break it down to two glucose molecules. Sucrose is essentially two 6-carbon sugars linked together. That's all it is. And then a polysaccharide is starch or glycogen, where you have thousands upon thousands, maybe millions of glucose molecules linked together. Many, many, many of those linked together. And so there's what glucose looks like. It's a 6-carbon sugar. The black atoms are the carbons, the reds are the hydrogens, and the reds are the oxygens, and the silver are the hydrogens. And generally, we deal with C6H12O6, 6 carbons, 12 hydrogens, 6 oxygens. This is the monomer of the carbohydrates, and it's all about glucose for us. That is what, that's why the monosaccharide is so important to us. Everything that we eat involving carbohydrates will ultimately get knocked down to glucose because we can't process sucrose for energy. We have to break it apart. We can only process the 6-carbon sugar, not the 12-carbon sugar. So, and that's what your monosaccharides look like. Glucose, this is what you get in this is fructose. This is a 6-carbon sugar. This is what you get in when you drink a Coke. And galactose is just a variation on both of these. So again, they're all 6-carbon sugars. So, and that is a great place to start. So anybody have any questions on this? So, okay, then I'm gonna pull the plug and I'll get us out of here. Lab this afternoon for the Tuesday lab is going to be looking at the human skull. So I'll see you all then.